this is the last problem that I solved, and I just want to point out that we know which way this equilibrium is going to shift because we're giving only initial concentrations of the reactant here, and we know we don't have any product, so it will definitely shift to the right, so that we were able to determine that we have to add reactant, or that's going to have a positive change for the product here, and it's going to have a negative change for the reactant. What if I gave you a reaction mixture that is not at equilibrium and you needed to determine which way this equilibrium shifts? You can do that very simply by determining the quotient here, the equilibrium quotient, which is the same calculation as an equilibrium constant here, whether it's QC or QP, or pressures or concentrations of molarity. It's set up the same way, but the value of QC is either going to be larger than or smaller than K, and so if it's larger than K, it's going to shift to the left, back to the reactant side, and if it's smaller than K, it's going to have to shift towards the product side or the right side, and then, well, and probably won't give it to you that it's equal to, because then you don't have a calculation to do. So for example, if I gave you this problem here, a reaction mixture containing phosphorus, not phosphorus, that's the pressure of I2, Cl2, and ICl. So we don't know which way it's going to shift. Is it going to shift to the left or to the right? We're provided with Kp, so we can simply calculate Qp then. Qp is going to be equal to the pressure of ICl squared, which is 0.355 squared, divided by the concentration of I2, which is 0.114, and times, not the concentration, this is the pressure, this is all in ATM, 0.102 ATM. I'm leaving the units out, they're always going to cancel. This would be ATM squared, and this would be ATM squared. So P here has no units, but when you do this, you end up with a quotient that's smaller than Kp, so we know this is going to shift to the right. The number here is 10.8. Again, that's smaller than, it's going to shift to the right. Okay, so let's work this problem keeping the reaction quotient in mind. Now we're given Kc, and we're told that the initial concentration of N2, which is a reactant, and O2, which is a reactant, are 0.200 m. Find the equilibrium concentration of the reactants and the products at this temperature, meaning we keep this constant, that's important, or otherwise Kc changes. This is easy, it's going to shift to the right because we don't have any concentration of NO, and if you were to calculate Qc, then you would have an initial concentration of NO squared, which is 0 squared, so that's right there, 0, no matter what you divide it by. So this is smaller than Kc, which means it is going to shift to the right, or this way. Now we can set up an ice table. The initial concentration of N2 is 0.200. The initial concentration of O2 is also 0.200, and then our product, which is NO, doesn't have a concentration. The change is going to be minus x, and plus 2x. Need to put that 2 here so that you can see that. So it's going to go up by 2 moles. And so our final concentrations, or the equilibrium concentrations, is going to be 0.200 minus x, 0.200 minus x, and 2x squared. 2x. Okay, now I'm going to square this once I plug it into the equilibrium expression. So Kc, which I'm given here, is 0.10 equals 2x squared divided by 0.200 minus x times 0.200 minus x, which is also squared. That makes my algebra a little bit easier. I can take the square root of both sides here. So I get the square root of 0.10 equals 2x divided by 0.200 minus x. I'm going to run out of space with my algebra, but that's okay, so I'll do a little bit of it, times 0.200 minus x. That's the square root of 0.1 times 0.200 minus x. So you just have to multiply that out. This is basic algebra. I guess I won't show you all of it. I have the solution for it. You should be able to work through it yourself. And then once you do that, so here's the ice table we worked out. That's the most difficult part. We didn't really need this because we knew it was going to shift to the right. And then we end up solving for x, which is 0.027. And what is it actually asking for? Find the equilibrium concentration. So you can then, in order to find the equilibrium concentrations, you just have to subtract 0.027 from 0.2, and then 2 times that would be the concentration of NO at equilibrium. You can plug that in to the equilibrium expression just to verify, and you should end up with 0.1. So here's a problem for you to consider. I'm not going to work it for you. I think it will help you. If you do want me to help you with it, you got to come by my office hours. But it's the same reaction, except this time we are told that we only have the product as a concentration. So this is going to shift to the left. And then when you set this up, when you set up your ice table, I'll give you one hint. You actually are going to end up with an equation where you have to use the quadratic equation to solve for x. You're going to end up with something that's 2x squared plus x plus some number, and so in order to solve for x you have to use the quadratic equation. Sorry, it happens occasionally. Alright, let's practice setting up ice tables some more. Here we have a reaction, 2 moles of N2O4 going to 2 moles of NO2. A reaction mixture at 100 degrees contains only products, 0.1 molar NO2, but no reactants, so we don't have to figure out what Q is because it's going to be infinitely large, therefore it's going to shift to the left. So I'm going to set up my table here. N2O4 goes to 2NO2, ICE, 0 initially, 0.100 M of the product. So that's going to go down by 2x. This is going to go up by x. I bring it all down, x, and this will be 0.100 minus 2x. If I put this into Kc, we have 0.100 minus 2x squared divided by x. So let's first multiply out the 0.100 minus 2x, so you get a squared, which is 0.0100 plus 2x squared, which is 4x squared, right? So 2x squared, the whole thing goes, it's a squared plus b squared minus 2ab, and then minus 0.1 times 2 squared, which is 0.400x divided by x. And now when you multiply that all out, you will have to use the quadratic equation, but you should do the rest of this yourself. But then I get, and I'll show you on the next page, you end up with this equation if you set it up to 0. Since we don't know what Kc is, we're provided here with the value 0.0100 0.36, we get a number for that. And just as a reminder, and for the exam, I'm going to give you the quadratic equation. You just need to know when to use it. Let's work the next problem, or you work the next problem here, right? So here we have the same reaction, but we have different concentration. This time we have, and you also will need to use the quadratic equation. I think this time you'll have a shift to the right, because you only have reactants, and so it's going to be set up the same way I set up this table here, the exact same way, except it'll be minus x and plus 2x. Okay, so that's all I'm going to say.